Yeah, okay. So, our next speaker is Avinash. So, he is currently first year MSc Mathematics student at IIT Madras. He has attended MTTS Level 1 at IIT Madras in 2023. So, his topic is Proof of Urysohn Lemma using the density of dyadic rationals in R. Over to you, Avinash.
Yeah. So let's start the proof of Urysohn's lemma by using the density of dyadic rationals. Let's see what is the Urysohn's lemma first. Urysohn's lemma is a topological lemma, and it is actually well known. It is used to prove the Tietz extension theorem and the Urysohn's metrization theorem. So it's related to the normal spaces. So let's see what are the normal spaces first. So if I have a topological space, let's say X, then I will say that X is normal if given any two non-empty disjoint closed sets, let's say A and B, then I can find the pair of open disjoint sets U and V such that A will be the subset of U and B is the subset of V. So that means we can separate the non-empty disjoint closed sets by using the open sets. So the examples of normal spaces are metric spaces. They are uh, then also if we take a lower limit topology on R, it is the example of normal space. Then so now let's see what are the dyadic rationals. So the rational numbers whose denominator is a power of 2 are the dyadic rationals, and they are actually dense in R because suppose if you have taken a two real numbers A and B such that A is less than B, then by the Archimedean property, I know that I can find a natural number such that 2 will be less than n into b minus a. So that means since my n is less than 2 to the power n, my 2 will be less than 2 to the power nb minus 2 to the power na. So by multiplying 2 to the power n to b and a, I have increased the distance between b and a greater than 2. I mean, I have made the distance greater than 2 so that I can find the integer in between 2 to the power na and 2 to the power nb. So suppose if we take m is equals to 2 to the power nb minus 1, greatest integer function of 2 to the power nb minus 1, then my m will be between 2 to the power na and 2 to the power nb. So my m by 2 to the power n will be in between a and b. So this says that my dyadic rationals are dense in R. Yeah. So before going to the Urysohn's lemma, let's see a few of the prepositions which are important to prove the Urysohn's lemma. So if I have a X to be a topological space, then X is normal if and only given any non-empty closed set A and the open set V containing A, there exists an open set U such that A subset of U and U closure subset of V. So let's see the proof of this. Suppose X is normal, A is non-empty closed set in X and V is open set containing A. So since V is open, V complement will be closed, and since A is contained in V, my A and V complement will be disjoint. So since my X is normal, I know that there exist open sets U and V such that U and V, there exist open sets U and W such that U and W are disjoint, and my A is contained in U and V complement is contained in W. Now U and W are disjoint, so therefore U is contained in W complement, and also since W is open, my W complement is closed. Now U is contained in W complement and W complement is closed, and since U closure is the smallest closed set containing U, my U closure will be the subset of W complement. And since V complement is subset of W, my W complement will be the subset of V. So I get that I know that A is subset of U and U is subset of U closure, and I got that U closure is subset of V. So therefore, uh, we proved the first implication. Now let's assume contrary, and let us consider the two non-empty disjoint closed sets of x, let's say a and b. So again, my b is closed, so that's why x minus b will be open, and since a and b are disjoint, a will be the subset of x minus b. So therefore, there exists a open set U such that a subset of U and U closure subset of B complement. Now B complement is subset of B complement is a superset of U closure. So therefore, B is a subset of complement of U closure, and U closure is closed. So that's why U closure complement is open. And again, U intersection with U closure complement is empty. So what we get, the two open sets U and complement of U closure such that one contains A and other contains B, and both are disjoint. So we proved that X is normal. Yes. Now let's see the Urysohn's lemma. So what does the Urysohn's lemma says? If I have a normal space, let's say X, then if I take any two non-empty disjoint closed sets in X, I can separate them by using the continuous function. So let's see how we can do this. Uh, if we have a two non-empty disjoint closed sets A and B, then there will exist a continuous map f from X to R such that f will take the values between 0 and 1, and on A f attains the value 0, and on B f attains only the value 1. So let's see the proof of this. So suppose S is the set of all the dyadic rationals in 0, 1. So how we will prove the Urysohn's lemma? To each dyadic rational R in S, we will assign some open set UR in X such that for all R in S, a subset of UR and UR closure will be the subset of B complement. And if my R is less than S, then UR closure will be the subset of US. So, and after this, we will define the continuous map F. So let's do the first claim. Yeah, suppose we have no, we have the A to be the closed set, and B is also the closed set. So that's why B complement is the open set. And since A and B are disjoint, A will be the subset of B complement. And by the previous lemma, since X is normal, we know that there exists a open set U, let's say U one half, such that A subset of U one half and U one half closure will contain in B complement. Again, A is closed and U one half is open, and A is contained in U one half. So there will exist some open set U1 by 4 such that A subset of U1 by 4 and U1 by 4 closure subset of U1 half. And similar for U1 half closure and B complement, there will exist some open set U3 by 4 such that U1 half closure subset of U3 by 4 and U3 by 4 closure subset of uh, B complement. So from above two inclusions, we have a subset of U1 by 4 and so on, U3 by 4 closure subset of B complement. Now continuously doing this, at the nth step, we will get the inequality, we will get the inclusions a subset of U1 by 2 to the power n and so on, U2 to the power n minus 1 by 2 to the power n closure will be the subset of B complement. Now, for all R in S, A subset of UR and UR closure subset of B complement will satisfy, because the way we have constructed our assignment satisfies this. Let R and S are the two elements of S, and let R is a less than S. Now UR closure will be the subset of US because I know that R and S are the dyadic rationals, so they will be in the form of m by 2 to the power n and k by 2 to the power l. And now at the n plus l stage, I know that there are the finite number of, in between R and S, there are the finite number of dyadic rationals whose denominator is 2 to the power n plus l. So that's why there will be the finite number of sets in between UR closure and US. So therefore, UR closure will be the subset of US. Now let's define the function f. So before that, let's take some notation. Let dx be the set t belongs to S such that x is not in ut. And let's define the function f by f from x to r such that if my x is in all of ut, then I will say that fx takes the value 0. And if there exists some t such that my x is not in ut, then I will define dx by, then I will define f of x by the supremum of dx. So fx is always well defined because dx is a subset of s, and s is bounded in open interval 0 1. So the supremum of dx always exists. Now from the definition it is clear that f takes the values between 0 and 1, and for all r in S we know that a is a subset of ur, so on a f takes the value 0. Now for all r in S ur is a subset of b complement, so therefore if we take any element of b, it will be not in ur because it is not in b complement. So therefore the dx for the x in b is actually the whole of s. So therefore f of x will be the supremum of s. So therefore on b the function will take the value only 1. Now before seeing the continuity of f, we have to see one remark, and it is very useful in proving the Urysohn's lemma. We will use it several times. So if my s is a dyadic rational and my x is in x, and if my s is less than fx, then f of x, then x will not be the element of US closure. And since it is not the element of US closure, it will not in US also. And hence x is not in US. S will be the element of dx. So let's see the proof of this. Suppose s is less than f of x. So since s is less than the supremum of dx, s is not the upper bound of dx. So there will exist some element in dx, let's say q, such that q will be in between s and supremum of dx. Now q is in dx, so therefore x will not be the element of uq. Hence x will not be the element of us closure because us closure is a subset of uq. So therefore x is not the element of us closure, hence it's not the element of us, hence s will be the element of dx. Now let's see the continuity of f. So we will prove that f is continuous by in a three cases. Suppose my x is in x, so we will take the three cases. First case will be the f of x is in open interval 0 1. Then we will take the case of f of x is equals to 0, and then f of x is equals to 1. Now let us assume that f of x is between 0 and 1, and let epsilon is greater than 0. So what we have to do, we have to produce some open neighborhood of x such that on that neighborhood my f will take the values between the epsilon neighborhood of f of x. Now I know that f of x is greater than 0. So therefore there is some r in s such that x is not in ur. So therefore f of x will be the supremum of dx, where dx is the set t in s such that x is not in ut. Since S is dense in open interval 0 1, I know that there will exist some S and R such that S will be between fx minus epsilon and fx, and R will be between f of x and f of x plus epsilon. Now S is less than f of x. So therefore, by the previous remark, what do I know? X is not in US closure. So therefore, X will be the element of US closure complement, and US closure complement is also the open set. So we will see that is this set can be used for our purpose. So let's see some more things. So x is not in US closure complement, and also f of x is strictly less than r. So therefore r is greater than the supremum of dx. So therefore r is not the element of dx, and hence x will be in a ur. So therefore x is in ur intersection US closure complement, and since both sets are open, ur minus US closure is also open set. Now, what we are claiming, any element of ur minus us closure takes the values between fx minus epsilon and fx plus epsilon. So let's take y belongs to ur minus us closure. Since y is not the element of us closure, it is not in us. Hence, s is belongs to dy. So therefore, it will be less than f of y. Now, y is the element of ur. So therefore, r is not in dy. So therefore, f of y will be less equal r. So this is again by the, yeah, my f of y is the supremum of dy, na. So therefore, r will be greater equal f of y. Now f of y is between s and r. So therefore, it is in a open interval fx minus epsilon to f of x plus epsilon. So therefore, f is continuous at x. Now let's take the next case. Suppose f of x is equal to 0 and let epsilon is greater than 0. So since this s is dense in open interval 0, 1, there will some element, let's say r in s, which will be in between 0 and epsilon. Now x is in ur because f of x is equal to 0. That means my x is in each ur. So that's why x is in ur. Now if y is element of ur, then r will not be in dy. This is by the definition of dy. So therefore f of y will be less equal r. Yeah, why f of y is less equal r? Because if my r is less than f of y, I know that r is the element of dy. That I actually proved in the lemma. So in this remark, I proved that if my s is less than fx, then s is the element of dx. So therefore, yeah. So therefore, r must be greater or equal f of y. So therefore, f of y is in the neighborhood of 0. Hence, f is continuous at x. So that means on the ur, on this open set ur, f takes the values between fx minus epsilon to f of x plus epsilon. So therefore, f is continuous at x. Now let's assume that f of x is equal to 1 and let epsilon is greater than 0. So I know that S is dense in open interval 0, 1. So there will exist some element in S that will lie between 1 minus epsilon to 1. Now S is less than f of x. So therefore x is not in US closure by the same remark. So therefore x will be in a complement of US closure. Now if my y belongs to complement of US closure, y is not in US closure, hence y is not in US. Hence by the definition of dy, I know that y will be the element of dy. So therefore, s will be the less equal to supremum of dy. So that's why s will be less equal f of y. Now let f of y. So therefore, we have got that f of y is between s and 1. So therefore, f of y is in the neighborhood, epsilon neighborhood of 1. So therefore, on the set US closure complement, f takes the values between f of x minus epsilon to f of x plus epsilon. So we have found the neighborhood around x that that gives us f is continuous at x. Yes. So therefore, the function f is continuous. So I have proved the Urysohn's lemma. So these are some references I used. Uh, so thank you. Is if anyone have any question, you can ask me.
Yeah, thank you, Avinash. It was nice presentation. So if anybody has any question, they can ask now.
Yeah, Avinash, you said mm, fluidic rationals are dense, right?
Yes. Yeah.
What about periodic rationals? I mean, for other values of P?
Periodic rationals.
Yeah,
So periodic rationals mean I don't know what are they, but they may be like m by p to the power n, where p is a fixed prime. Na? You want to say this?
yeah, yeah.
So yeah, they will also be dense in R because yeah, by the same thing we can do this because yeah, by taking p to the power n, we can increase the distance between b and a so that there will be some integer in between them, and hence we will again get the same that a will be less than m by p to the power n will be less than b.
Yeah, it seems so. Yeah. So viewers can verify this thing if this thing is working or not. It seems that it is working. Yeah, I'm done.
Yes.